Sharp distinctions between lengths, areas, and volumes, but they're all just real numbers to us, equations as curves. To be sure, Fermat and Descartes never used the XY plane to study anything as tangible as cinnamon raisin bread. For them, the XY plane was a tool to study pure geometry. Working separately, they each noticed that any linear equation, meaning an equation in which x and y appear to the first power only, produced a straight line on the XY plane. This connection between linear equations and lines suggested the possibility of a deeper connection, one between nonlinear equations and curves. In a linear equation like y equals 200x, the variables x and y appear on their own, unadulterated, and do not get squared or cubed or raised to any higher power. Fermat and Descartes realized they could play the same game with other powers and other equations. They could cook up any equation they desired and do whatever they wanted to x and y, square one of them, cube the other, multiply them together, add them, whatever, and then interpret the result as a curve. With any luck, it would be an interesting curve, maybe one that nobody had ever imagined, maybe one that Archimedes had never studied. Any equation with x and y in it was a new adventure. It was also a Gestalt switch. Instead of starting with a curve, you start with an equation and see what kind of curve it makes. Let algebra drive and put geometry in the back seat. Fermat and Descartes began by looking at quadratic equations. These are equations in which, along with the usual constants, like 200, and linear terms like x and y, the variables can also get squared or multiplied together, creating quadratic terms like x squared, y squared, and xy. In Latin, quadratus means square. Squared quantities had traditionally been interpreted as the areas of square regions. Thus, x squared meant the area of an x by x square. In the old days, an area was seen as a fundamentally different kind of quantity from a length or a volume. But to Fermat and Descartes, x squared was just another real number, which meant it could be graphed on a number line, just as x or x cubed or any other power of x could be. Today, students in high school algebra are routinely expected to be able to graph equations like y equals x squared, whose associated curve turns out to be a parabola. Remarkably, all other equations involving quadratic terms in x and y, but no higher powers, give curves of just 4 possible types: parabolas, ellipses, hyperbolas, or circles, and that's it. Except for some degenerate cases that yield lines, points, or no graph at all, but these are rare oddities that we can safely ignore. For example, the quadratic equation xy equals 1 gives a hyperbola, while x squared plus y squared equals 4 is a circle and x squared plus 2y squared equals 4 is an ellipse. Even a quadratic as beastly as x squared plus 2xy plus y squared plus x plus 3y equals 2 has to be one of the 4 possibilities above. It turns out to be a parabola. Fermat and Descartes were the first to discover this wonderful coincidence. The quadratic equations in x and y are the algebraic counterparts of the conic sections of the Greeks, the 4 kinds of curves obtained by slicing through a cone at different angles. Here, in Fermat's and Descartes' new arena, classical curves were reappearing like ghosts from the mist, better together. The newfound ties between algebra and geometry were a boon to both subjects. Each could help the other compensate for its deficits. Geometry appealed to the right side of the brain. It was intuitive and visual, and the truths of its propositions were often clear at a glance, but it called for a certain kind of ingenuity. With geometry, there was often no clue about where to start a proof. Beginning an argument required strokes of genius. Algebra, however, was systematic. Equations could be massaged almost mindlessly, peacefully. You could add the same term to both sides of an equation, cancel common terms, solve for an unknown quantity, or perform a dozen other procedures and algorithms according to standard recipes. The processes of algebra could be soothingly repetitive, like the pleasures of knitting, but algebra suffered from its emptiness. Its symbols were vacuous. They meant nothing until they were given meaning. There was nothing to visualize. Algebra was left-brained and mechanical. Together, though algebra and geometry were unstoppable, algebra gave geometry a system. Instead of needing ingenuity, it now demanded tenacity. It transformed difficult questions requiring insight into straightforward, if laborious, calculations. The use of symbols freed the mind and saved time and energy. For its part, geometry gave algebra meaning. Equations were no longer sterile. They were now embodiments of sinuous geometric forms. A whole new continent of curves and surfaces opened up as soon as equations were viewed geometrically. Lush jungles of geometric flora and fauna waited to be discovered, catalogued, classified, and dissected. Fermat versus Descartes. Anyone who has studied a lot of math and physics will have run into the names of Fermat and Descartes. But none of my teachers or textbooks ever told me about their rivalry or how vicious Descartes could be. To understand what was at stake in their fights, You need to know more about their lives, their personalities, and what they hope to achieve. René Descartes, 1596–1650, was one of the most ambitious thinkers of all time. Daring, intellectually fearless, and contemptuous of authority, he had an ego as big as his genius. For example, of the Greek approach to geometry, which all other mathematicians had revered for 2,000 years, he wrote dismissively, "What the ancients have taught us is so scanty, and for the most part so lacking in credibility, that I may not hope for any kind of approach toward truth, except by rejecting all the paths which they have followed." At a personal level, he could be paranoid and thin-skinned. The most famous portrait of him shows a man with a gaunt face, haughty eyes, and a snide little moustache. He looks like a cartoon villain. Descartes set out to rebuild human knowledge on a foundation of reason, science, and skepticism. He is best known for his work in philosophy, immortalized by his famous line cogito, ergo sum, I think, therefore I am. In other words, when all is in doubt, at least one thing is certain: the doubting mind exists. His analytic approach, which appears to have been inspired by the rigorous logic of mathematics, is widely seen today as the beginning of modern philosophy. In his most famous book, his Discourse on Method, Descartes introduced a bracing new style of thinking about philosophical problems, but he also included 3 appendices of interest in their own right: one on geometry, in which he presented his approach to analytic geometry; another on optics, of great import at a time when telescopes, microscopes, and lenses were the latest technology; and a third on weather, which has mostly been forgotten except for his correct explanation of rainbows. His capacious intellect roamed far and wide. He viewed the living body as a system of mechanical devices and located the seat of the soul in the brain's pineal gland. He proposed a grand, but wrong, system of the universe according to which invisible vortices pervaded all space, with the planets carried along like leaves in a whirlpool. Born into a wealthy family, Descartes was sickly as a little boy and was allowed to stay in bed and read and think as long as he liked, a habit he kept his whole life, never rising before noon. His mother died when he was just a year old, but fortunately she left him a sizable inheritance that later allowed him to live a life of leisure and adventure as a wandering gentleman. He volunteered for the Dutch army but never saw combat, and he had plenty of time for philosophy. He spent much of his adult life in Holland, working on his ideas and corresponding and bickering with other great thinkers. In 1650, he reluctantly took a position in Sweden, which he scorned as the country of bears amid rocks and ice, as Queen Christina's personal philosophy tutor. Unfortunately for Descartes, the energetic young queen was an early riser. She insisted on lessons at 5 in the morning, an ungodly hour for anyone but especially for Descartes, accustomed to getting up at noon his whole life. That winter in Stockholm was the coldest in decades. After a few weeks, Descartes caught pneumonia and died. Pierre de Fermat, 1601–1665, who was 5 years younger than Descartes, lived a peaceful, upper-middle-class, comparatively uneventful life. By day he was a lawyer and provincial judge in Toulouse, far from the hubbub in Paris. By night he was a husband and father. He came home from work, ate dinner with his wife and 5 kids, and then spent a few hours with his one true passion, doing math. Whereas Descartes was a big thinker of colossal ambitions, Fermat was a shy man, quiet, even-tempered and naive. He had more modest goals than Descartes did. He didn't see himself as a philosopher or a scientist. Math was enough for him. He pursued it as an amateur lovingly. He saw no need to publish, and he didn't. He wrote little notes to himself in the books he was reading, classic Greek tomes by Diophantus and Archimedes, and occasionally mailed his ideas to scholars he thought might appreciate them. He never traveled far from Toulouse or met any of the major mathematicians of his day, although he corresponded with them through Marin Mersenne, a Franciscan friar, mathematician, and social connector. It was through Mersenne that Fermat and Descartes locked horns. Among mathematicians, Mersenne was the go-to guy in Paris. In a time before Facebook, he kept everyone in touch with everyone else, a real busybody with a certain lack of tact and discretion. He had a way of stirring up trouble. For example, he showed people personal letters he received and released confidential manuscripts before they were published. There was a circle around him of top mathematicians, not quite in the same league as Fermat and Descartes, but strong nonetheless, and they apparently had it in for Descartes. They were always sniping at him and his grandiose discourse on method. So when Descartes heard via Mersenne that some nobody in Toulouse, some amateur named Fermat, claimed to have developed analytic geometry a decade earlier than he had, and that this same amateur, who was this guy, had raised doubts about his theory of optics, Descartes considered it another case of someone out to get him. In the years to come, he fought vehemently against Fermat and tried to ruin his reputation. After all, Descartes had a lot to lose. In the discourse, he'd claimed that his analytical method was the one sure route to knowledge. If Fermat could outdo him without even using his method, his whole project was at risk. Descartes badmouthed Fermat mercilessly and to some extent succeeded in diminishing him. Fermat's work was never properly published until 1679. His results trickled out through word of mouth or in copies of his letters, but he was not truly appreciated until long after his death. Descartes, however, hit it big. His discourse became famous. The next generation learned analytic geometry from it. Even today, our students learn about Cartesian coordinates, even though Fermat came up with them first. The search for analysis, the long-lost method of discovery, the squabbles between Descartes and Fermat, took place against the backdrop of the early 17th century, a time when mathematicians dreamed of finding a method of analysis for geometry. Here analysis, as in analytic geometry, is to be understood in the archaic sense of the word, as a means of discovering results rather than proving them. There was widespread suspicion at the time that the ancients had possessed such a method of discovery, but had deliberately concealed it. Descartes, for example, alleged that the ancient Greeks had knowledge of a species of mathematics very different from that which passes current in our time. But my opinion is that these writers then, with a sort of low cunning, deplorable indeed, suppressed this knowledge. Symbolic algebra seemed like it might be this long-lost method of discovery. But in more conservative quarters, algebra met with reactionary skepticism. A generation later, when Isaac Newton said, "Algebra is the analysis of the bunglers in mathematics," he was throwing a thinly veiled insult at Descartes, the prime example of a bungler who had relied on algebra as a crutch to solve problems by working backward. In launching his attack, Newton was adhering to a traditional distinction between analysis and synthesis. In analysis, one solves a problem by starting at the end, as if the answer had already been obtained, and then works back wishfully toward the beginning, hoping to find a path to the given assumptions. It's what kids in school think of as working backward from the answer to figure out how to get there. Synthesis goes in the other direction. It starts with the givens, and then, by stabbing in the dark, trying things, you are somehow supposed to move forward to a solution, step by logical step, and eventually arrive at the desired result. Synthesis tends to be much harder than analysis, because you don't ever know how you're going to get to the solution until you do. The ancient Greeks regarded synthesis as carrying more logical force, more persuasive power than analysis. Synthesis was considered the only valid way to prove a result. Analysis was a practical way to find the result. If you wanted a rigorous demonstration, you had to do synthesis. That's why, for example, Archimedes used his analytical method of balancing shapes on seesaws to find his theorems, but then switched to the synthetic method of exhaustion to prove them. Still, although Newton looked down his nose at algebraic analysis, we will see in Chapter 7 that he used it himself, and to tremendous effect. But he wasn't its first master. Fermat was. Fermat's style of thinking is fun to examine, because it's elegant and accessible, and yet foreign and surprising. His methods for studying curves are no longer in use, having been superseded by the more sophisticated techniques in the textbooks today. Optimizing for the overhead bin. Fermat's embryonic version of differential calculus grew out of his application of algebra to optimization problems. Optimization is the study of how to do things in the best possible way. Depending on context, best might mean fastest, cheapest, biggest, most profitable, most efficient, or some other notion of optimality. To illustrate his ideas in the simplest fashion, Fermat contrived a few problems that sound a lot like the exercises we math teachers are still assigning to our students today. They can blame it all on him. One of those problems, updated for our time, goes something like this. Imagine you want to design a rectangular box to hold as much stuff as possible, subject to two constraints. First, the box has to have a square cross-section, x inches wide by x inches deep. Second, it has to fit in the overhead bin of a certain airline. According to their rules for carry-on baggage, the width plus depth plus height of the box cannot exceed 45 inches. What choice of x produces a box of maximum volume? One way to solve this is with common sense. Try a few possibilities. Say the width and depth are 10 inches each. That would allow for a height of 25 inches, since 10 plus 10 plus 25 equals 45. A box with those dimensions would have a volume of 10 by 10 by 25, which equals 25 cubic inches. Would a cube-shaped box be better? Since a cube must have equal height, width, and depth, it would have to have dimensions 15 by 15 by 15, which multiplies out to a roomy cubed, 375 cubic inches. Fiddling around with a few other possibilities makes it seem likely that a cube is the optimal choice for the shape of the box. And indeed it is. So this is not a particularly hard problem in itself. The point of it is to show how Fermat reasoned about such problems, because his approach led to much greater things. As in most algebra problems, the first step is to translate all the given information into symbols. Since the width and depth of the box are both x, they add up to 2x. And since the height plus width plus depth cannot exceed 45 inches, that leaves 45 minus 2x for the height. Thus the volume will be x times 45 minus 2x. Multiplying that out gives 45x squared minus 2x cubed. That's the volume of our box. Call it v, x. Thus Vx equals 45x squared minus 2x cubed. If we cheat momentarily and use a computer or a graphing calculator to plot x horizontally and v vertically, we see that the curve rises up and reaches its maximum when x equals 15 inches, as expected, and then descends back to 0. Alternatively, to find that maximum with differential calculus as practiced today, our students would reflexively take the derivative of v and set it equal to 0. The thinking is that at the top of the curve the slope is 0. The curve is neither rising nor falling there. So since the slope is measured by the derivative as we'll see in Chapter 6, the derivative must be 0 at the maximum. After a bit of algebra and the incantation of various memorized rules for derivatives, this line of reasoning would also yield x equals 15 at the maximum. But Fermat didn't have graphical calculators or computers, and he certainly didn't have the concept of derivatives. On the contrary, he invented the ideas that led to derivatives. So how did he solve the problem? He used a special property of the maximum. Horizontal lines below the maximum intersect the curve at 2 points, as shown here, whereas horizontal lines above the maximum don't intersect the curve at all. That suggested an intuitive strategy to solve the problem. Imagine slowly lifting a horizontal line that starts below the maximum. As the line gradually moves up, its 2 intersection points slide toward each other along the curve like beads on a necklace. At the maximum, those 2 points collide. Looking for that collision was how Fermat determined the maximum. He derived 1000, 500, 2000, 25, 0, 3000, 35, 0, volume a condition for 2 points to merge into one, forming what's known as a double intersection. With that insight in place, the rest is algebra, the mere manipulation of symbols. It goes as follows. Say the 2 intersections occur at x equals A and x equals b. Then since by construction, they lie on the same horizontal line, we must have v of a equals v of b, hence 45a squared minus 2, a cubed equals 45b squared minus 2b cubed. To make headway, it helps to rearrange this equation. If we put the squares on one side and the cubes on the other, we get 45a squared minus 45b squared equals 2a cubed minus 2b cubed. With some skill in high school algebra, we can then factor both sides to obtain 45 times a minus b times a plus b equals 2 times a minus b times a squared plus a b plus b squared. Next, divide both sides by the common factor of a b that's legal, since a and b are assumed to be different. If they were equal, dividing both sides by a b would amount to dividing by 0, which is prohibited, as discussed in Chapter 1. After cancellation, the resulting equation is 45 times a plus b equals 2 times a squared plus a b plus b squared. Buckle up now for a confusing point of logic. Fermat has just assumed that a and b are not equal. Yet he goes on to imagine that the equation he has just derived will continue to hold when a and b do become equal as they merge at the maximum. He tries to justify this by invoking a murky concept he calls adequality. It expresses the idea that a and b become sort of equal but not really equal at the maximum. Today we would phrase it using the concept of a limit or a double intersection. Anyway, he sets a is approximately b, where the squiggly equals sign means adequal, and then cavalierly substitutes a for b in the equation above to get 45 times 2, a equals 2 times a squared plus a squared plus a squared. This simplifies to 90 a equals 6 a squared, whose solutions are a equals 0 and a equals 15. The first of these solutions, a equals 0, gives a box of minimum volume. It has 0 width and depth and hence has 0 volume. That's of no interest. The second solution, a equals 15, gives the box of maximum volume. There's the answer we've been expecting. 15 inches is the optimal width and depth. From today's perspective, Fermat's reasoning seems strange. He finds a maximum without using derivatives. Today we teach derivatives before optimization. Fermat did it the other way around, but it doesn't matter. His ideas are equivalent to ours. How Fermat helped the FBI. The legacy of Fermat's early work on optimization is all around us. Our lives today depend on algorithms that solve optimization problems using the notion of double intersections and equivalent conditions expressed with derivatives. Today's problems tend to be much more complicated than Fermat's, but the spirit is the same. One important application involves big data sets, where it's often helpful to code the data as compactly as possible. For example, the Federal Bureau of Investigation has millions of records of fingerprints. To store them, search them, and retrieve them efficiently for background checks, they use calculus-based methods of data compression. Clever algorithms reduce the size of the digitized fingerprint files without sacrificing any details that matter. The same is true when you store music and pictures on your phone. Rather than keep every note and pixel, compression algorithms named MP3 and JPEG save space by distilling the information down to a much more efficient form. They also let us download songs and photos quickly and send them to our loved ones without clogging up their inboxes too much. To see what calculus and optimization have to do with data compression, let's take a look at the related statistical problem of fitting a curve to data, an issue that comes up everywhere from climate science to business forecasting. The data set we'll examine shows how day length varies with the seasons. As we all know, the days are longer in the summer and shorter in the winter, but what does the overall pattern look like? In the graph below, I've plotted the data for New York City for the year 2018, with time running horizontally from January 1 on the far left to December 31 on the far right. The vertical axis shows the number of minutes between sunrise and sunset at different times of the year. To avoid cluttering up the picture, I've shown the data for only 27 days, sampled every 2 weeks starting on January 1. The graph shows that day length rises and falls throughout the year as expected. The days are longest around the summer solstice, June 21, corresponding to the peak at day 172 near the middle of the graph, and shortest around the winter solstice, half a year later. Overall, the data appear to lie on a smoothly undulating wave. In high school trigonometry classes, teachers talk about a certain kind of wave, a sine wave. Later in this book, I will have more to say about what sine waves are and why they are special from the standpoint of calculus. For now, the main thing we need to know is that sine waves are connected to circular motion. To see the connection, imagine a point moving around a circle at a constant speed. If we track its up and down position as a function of time, the point traces out a sine wave. And because circles are intimately connected to cycles, sine waves come up wherever cyclic phenomena occur, from the cycle of the seasons to the vibrations of a tuning fork to the 60-cycle hum of fluorescent lights and power lines. That annoying hum is the sound of sine waves bobbing up and down 60 times a second. It's the telltale sign of alternating current produced by generators in the power grid, whose machinery is spinning at that same frequency. Where there is circular motion, there are sine waves. Any sine wave is completely defined by 4 vital statistics: its period, average, amplitude, and phase. These 4 parameters have simple interpretations. The period t indicates how long it takes the wave to complete a full cycle. For the day-length data we're considering here, t is about a year or, to be more precise, 365.25 days. That extra quarter of a day is why we need leap years every 4th year, to keep the calendar in sync with natural cycles. The average of the sine wave is its baseline value. For our data, it's the typical number of minutes of daylight in New York City, averaged across all the days of the year 2018. The wave's amplitude tells us how many additional minutes of light there are on the longest day of the year as compared to the average day. The wave's phase c tells us the day on which the wave crosses upward through its average value, sometime around the spring equinox. It's helpful to think of these 4 parameters, a b, c, t, as 4 knobs we can turn to adjust various features of the sine wave's shape and location. The b knob moves the sine wave up or down, the c knob moves it left or right, the t knob controls how rapidly it oscillates, and the r knob determines how pronounced those oscillations are. If we could somehow set the knobs to make the sine wave go through all the data points we plotted earlier, that would amount to a significant compression of information. It would mean we were capturing the 27 data points with just the 4 parameters in the sine wave, thereby compressing the data by a factor of 27 over 4, or 6.75. Actually, since we know one of the parameters is a year, we really have only 3 parameters to fiddle with, giving us a compression factor of 27 over 3, or 9. A reduction of this size is conceivable because the data are not random, they follow a pattern. The sine wave embodies that pattern and does the work for us. The only catch is that there is no sine wave that goes through the data perfectly. That's to be expected when fitting an idealized model to real-world data. There are bound to be some discrepancies. The hope is that the discrepancies are negligible. To minimize them, we need to find the sine wave that hugs the data points as closely as possible. That's where calculus comes in. The figure below shows the best-fitting sine wave, as determined by an optimization algorithm I'll explain in a minute. But first, notice the resulting fit is not perfect. For instance, the wave doesn't quite dip down low enough in December, when the days are very short and the data fall below the curve. Nevertheless, a simple sine wave certainly captures the essence of what's going on. Depending on our goals, a fit of this quality may be adequate. So how does calculus come in? It helps us choose the 4 parameters optimally. Imagine turning the 4 knobs to get the best possible fit, somewhat like tuning the dial on a radio to get the strongest possible signal. This is essentially what Fermat did in the overhead bin problem when he found the roomiest dimensions for the box. In that case, he was tuning a single parameter, x, the side length of the box, and looking for a double intersection as a signal that the volume of the box was a maximum. In our case, we have 4 parameters to tune, but the basic idea is the same. We'll look for a double intersection and that'll give us our optimal choice of the 4 parameters. In a little more detail, here's how it works. For any given choice of the 4 parameters, we calculate the discrepancy, in other words, the error between the sine wave fit and the actual data at every one of the 27 points recorded throughout the year. A natural criterion for choosing the best fit is that the total error, summed over all 27 points, should be as small as we can make it. But total error is not quite the right concept, because we don't want the negative errors to cancel the positive ones and give the false impression that the fit has less error than it does. Undershoots are just as bad as overshoots, and both should be penalized. They shouldn't be allowed to cancel out. For this reason, mathematicians square the errors at each point to make the negative ones become positive. That way, they can't possibly produce any spurious cancellations. Here's one place where the fact that a negative times a negative is a positive is useful in a practical setting. It makes the square of a negative error count as a positive discrepancy, as it should. So the basic idea is to choose the 4 parameters in the sine wave in such a way that they minimize the total squared error of the fit to the data. Accordingly, this approach is called the method of least squares. It works best when the data follow a pattern, as they do here, all of which raises an extremely important general point. Patterns are what make compression possible in the first place. Only patterned data can be compressed. Random data cannot. Happily, many of the things people care about, like songs and faces and fingerprints, are highly structured and patterned. Just as day length follows a simple wave pattern, a photograph of a face contains eyebrows, blemishes, cheekbones, and other characteristic patterns. Songs have melodies and harmonies, rhythms and dynamics. Fingerprints contain ridges and loops and whirls. As human beings, we recognize these patterns instantly. Computers can be taught to recognize them too. The trick is to find the right kinds of mathematical objects to encode particular patterns. Sine waves are ideal for representing periodic patterns, but they are less well suited to representing sharply localized features, like the edge of a nostril or a beauty mark. For this purpose, researchers in several different fields came up with a generalization of sine waves called wavelets. These little waves are more localized than sine waves. Instead of extending periodically out to infinity in both directions, they are sharply concentrated in time or space. Wavelets suddenly turn on, oscillate for a while, and then turn off. They look almost like the signals on heart monitors or the bursts of activity recorded on seismographs during an earthquake. They are ideal for representing a sudden spike in a brainwave recording, a bold stroke on a Van Gogh painting, or a wrinkle on a face. The Federal Bureau of Investigation used wavelets to modernize their fingerprint files. From the time fingerprints were introduced, at the beginning of the 20th century, fingerprint records had been stored as inked impressions on paper cards. The files were difficult to search quickly. By the mid-1990s, the collection had grown to wavelet roughly 200 million fingerprint cards on file and occupied an acre of office space. When the FBI decided to digitize the files, they turned them into grayscale images with 256 different levels of gray at a resolution of 500 dots per inch, enough to capture all the fine whirls, loops, ridge endings, bifurcations, and other identifying minutiae of fingerprints. The problem, however, was that at the time, a single digitized card contained about 10 megabytes of data. That made it prohibitive for the FBI to send digital files quickly to local police. Remember, this was in the mid-1990s, when phone modems and fax machines were state-of-the-art, and transmitting a 10 megabyte file took hours. Plus, it was tough to exchange files that big when 1.5 megabyte floppy disks were the medium of choice. Given the growing demand for faster turnaround times on the 30,000 new fingerprint cards that flooded in every day with urgent requests for background checks, there was a desperate need to modernize the system. The FBI had to find a way to compress the files without distorting them. Wavelets were ideal for the job. By representing fingerprints as combinations of many wavelets, and by turning the knobs on them optimally using calculus, Mathematicians from the Los Alamos National Lab teamed up with the FBI to shrink their files by a factor of more than 20. It was a revolution for forensics. Thanks to Fermat's ideas in their modern form, along with an even greater role for wavelet analysis, computer science, and signal processing, a 10-megabyte file could be compressed to only 500 kilobytes, a manageable size to send over the phone lines. And it could be done without sacrificing fidelity. Human fingerprint experts nodded their approval. So did computers. The compressed files passed the FBI's automatic identification system with flying colors. It was good news for calculus and bad news for criminals, the principle of least time. I wonder what Fermat would have thought of this use of his ideas. He himself was never especially interested in applying mathematics to the real world. He was content to do math for its own sake. But he did make one contribution to applied mathematics of lasting importance. He was the first person to deduce a law of nature from a deeper law by using calculus as a logical engine. Just as Maxwell would do with electricity and magnetism 2 centuries later, Fermat translated a hypothetical law of nature into the language of calculus, started the engine and fed the law in, and out popped another law, a consequence of the first one. In so doing, Fermat, the accidental scientist, initiated a style of reasoning that has dominated theoretical science ever since. The story began in 1637, when a group of Parisian mathematicians asked Fermat for his opinion on Descartes' recent treatise on optics. Descartes had a theory about how light bent when it passed from air into water or from air into glass, an effect known as refraction. Anyone who has ever played with a magnifying glass knows that light can be bent and focused. In my youth, I liked to set leaves on fire by holding a magnifying glass over them on the driveway and lifting the glass up and down until the sun's rays focused into a tight white spot of blazing intensity, causing the leaf to smolder and eventually ignite. Refraction is used in less spectacular ways in our spectacles. The lenses in our eyeglasses bend and focus the light rays where they belong, at the right place on the retina to correct faulty vision. The bending of light also explains an illusion you may have noticed while lounging by a swimming pool on a sunny day. Suppose that at the bottom of the pool, there happens to be a shiny, tragically misplaced object like a piece of jewelry. You look down through the water at the shiny object, but it's not quite where it appears to be because the light rays bouncing off it get bent as they pass from water into air on their way out of the pool. For the same reason, a spear fisherman needs to aim below the apparent position of a fish to have a chance of hitting it. Refraction phenomena like these obey a simple rule. When a ray of light passes from a thinner medium like air into a denser medium like water or glass, the ray bends toward the perpendicular to the interface between the two media. When it passes from a denser medium into a thinner one, it bends away from the perpendicular, as illustrated here. In 1621, the Dutch scientist Willebrord Snell sharpened this rule and made it quantitative by doing a clever experiment. By systematically changing the angle O of the incoming ray and observing how the angle B of the outgoing ray changed in response, he discovered that the ratio sin always stayed the same for a given pair of media. Here sin refers to the sine function of trigonometry, the same sine function whose wavy graph appeared in our analysis of day length. However, Snell found that the value of sin did depend on what the two media were made of. Air and water produced one constant ratio, whereas air and glass produced another. He had no idea why the sine law worked. It just did. It was a brute fact about light. Descartes rediscovered Snell's sine law and published it in his 1637 essay Dioptrics, unaware that it had been found by at least 3 thinner denser medium others before him. Snell in 1621, the English astronomer Thomas Harriot in 1602, and the Persian mathematician Abu Sa'd al-Ala ibn Sal way back in 984. Descartes had given a mechanical explanation for the sine law in which he, incorrectly, assumed that light moved faster in a denser medium. To Fermat, that sounded upside down and contrary to common sense. Trying to be helpful, and being a naive and innocent fellow, Fermat offered what he thought were a few gentle criticisms of Descartes' theory, and mailed them back to the Parisian mathematicians who'd asked for his opinion. What Fermat did not know was that those mathematicians were Descartes' bitter enemies. They were using Fermat for their own sinister purposes, and as any teenager could have anticipated, when Descartes heard through the grapevine about Fermat's comments, he felt he was being attacked. He'd never heard of the lawyer from Toulouse. To him, Fermat was an obscure amateur working out in the countryside, someone easily dismissed as another gnat buzzing around his head. Over the next few years, Descartes treated Fermat condescendingly and claimed that he'd blundered into his results by accident. Fast forward 20 years. In 1657, after Descartes had died, Fermat was asked by a colleague named Marin Cureau de la Chambre to revisit the old controversy about refraction. Cureau's inquiry prompted Fermat to take a look at the problem himself, using what he knew about optimization. Fermat had a hunch that light optimized. More precisely, he guessed that light always followed the path of least resistance between any 2 points, which he took to mean that it traveled along the fastest possible route. He could see that this principle of least time would explain why light moved in a straight line in a uniform medium, and why, when it reflected off a mirror, its angle of incidence equaled its angle of reflection. But could the principle of least time also correctly predict how light bent when it passed from one medium into another? Would it explain the sine law of refraction? Fermat wasn't sure. The calculation wouldn't be easy. An infinite number of straight-line paths, each bent like an elbow at the infinitewers face, could take the light from a source point in one medium to a target point in the other. Computing the minimum of all those travel times was going to be difficult, especially at that embryonic stage in the development of differential calculus. There were no tools available other than his old double intersection method. Plus, he was afraid of getting the wrong answer. As he wrote to Cureau, the fear of finding, after a long and difficult calculation, some irregular and fantastic proportion, and my natural inclination to laziness left the matter in that state. 5 years passed while Fermat worked on other problems, but eventually his curiosity got the better of him. In 1662 he forced himself to do the calculation. It was arduous and unpleasant, but as he hacked away at the thicket of symbols he started to see something. The terms began to cancel, the algebra was working, and there it was, the sine law. In a letter to Cureau, Fermat called this calculation the most extraordinary, the most unforeseen, and the happiest one he'd ever done. I was so surprised at such an unexpected event that I can scarcely recover from my astonishment. Fermat had applied his embryonic version of differential calculus to physics. No one had ever done that before. And in so doing, he showed that light travels in the most efficient way, not the most direct way, but the fastest. Of all the possible paths light can take, it somehow knows, or behaves as if it knows, how to get from here to there as quickly as possible. This was an important early clue that calculus was somehow built into the operating system of the universe. Source target, the principle of least time, was later generalized to the principle of least action, where action has a technical meaning that we needn't go into here. This optimization principle, that nature behaves in the most economical way in a certain precise sense, was found to correctly predict the laws of mechanics. In the 20th century, the principle of least action was extended to general relativity and quantum mechanics and other parts of modern physics. It even made an impression on philosophy in the 17th century, when Gottfried Wilhelm Leibniz argued that all is for the best in the best of all possible worlds, an optimistic point of view later parodied by Voltaire in Candide. The idea of using an optimality principle to explain physical phenomena and to deduce its consequences with calculus began with this very calculation by Fermat. The tussle over tangents, Fermat's optimization techniques, also allowed him to figure out tangent lines to curves. This was the problem that really made Descartes' blood boil. The word tangent comes from a Latin root for touching. The terminology is apt, since instead of cutting across a curve in 2 places, a tangent line touches the curve at one point, barely grazing it. The condition for tangency is similar to that for a maximum or a minimum. If we intersect a curve with a line and then slide the line up or down continuously, tangency occurs when 2 intersections coalesce into one. By sometime in the late 1620s, Fermat was able to find the tangent line to essentially any algebraic curve, meaning a curve expressible solely in terms of whole number powers of x and y, without any logarithms, sine functions, or other so-called transcendental functions in it. Using his big idea of the double intersection, he could calculate everything with his methods that we can today with derivatives. Descartes had his own method of finding tangent lines. In his geometry of 1637, he proudly announced his method to the world. Unaware that Fermat had already solved the problem, Descartes independently hit on the double intersection idea, but he used circles instead of lines to cut through the curves of interest. Near the point of tangency, a typical circle would cut through the curve at 2 points, or at none. By adjusting the location and radius of the circle, Descartes could force the 2 intersection points to merge into one. At that double intersection, bingo, the circle intersected the curve tangentially. That gave Descartes everything he needed to find the tangent to the curve. It also gave him the normal to the curve, which lay at right angles to the tangent, along the circle's radius. Why his method was correct but clumsy, it generated bushels of algebra, much more than Fermat's. But Descartes hadn't even heard of Fermat yet, so in his usual cocksure fashion, he presumed he had outdone everyone. As he crowed in geometry, "I have given a general method of drawing a straight line making right angles with the curve at an arbitrarily chosen point upon it. And I dare say that this is not only the most useful and most general problem in geometry that I know, but even that I ever desired to know." Late in 1637, when Descartes learned from his correspondence in Paris that Fermat had beaten him to the solution of the tangent problem by about 10 years, but had never gotten around to publishing it, he was dismayed. In 1638 he studied Fermat's method, looking for holes. Oh, there were so many. Writing through an intermediary, he said, "I do not even want to name him so that he will feel less shame at the errors that I have found." He challenged Fermat's logic, which to be fair was sketchy and poorly explained. But eventually, after several letters back and forth, with Fermat calmly trying to clarify his ideas, Descartes had to concede that his reasoning was valid. But before admitting defeat, he tried to stump Fermat by challenging him to find the tangent line to a curve defined by the cubic equation x cubed plus y cubed equals 3xy, where a was a constant. Descartes knew that he himself couldn't find the tangent with his own clunky circle method. The algebra became unmanageable, so he was confident that Fermat wouldn't be able to find it with his line method. But Fermat was a stronger mathematician, and he had a better method. He dispatched Descartes' curve without breaking a sweat, much to Descartes' chagrin. Within sight of the promised land, Fermat paved the way for calculus in its modern form. His principle of least time revealed that optimization is woven deeply into the fabric of nature. His work on analytic geometry and tangent lines blazed a trail to differential calculus that others soon followed. And his virtuosity with algebra enabled him to find the areas under certain curves that had eluded even his most illustrious predecessors. In particular, he found the area under the curve y equals x to the n for any positive integer n, using little more than his bare hands. Others had solved the first 9 cases, n equals 1, 2, 9, but couldn't find a strategy that worked for all n. Fermat's advance was a giant step forward for integral calculus, one that would set the stage for breakthroughs to come. Yet for all that, his studies still fell short of the secret that Newton and Leibniz would soon discover, the secret that revolutionized and unified the two sides of calculus. It's a pity that Fermat missed it, for he came so close. The missing link was related to something he created, but never recognized as crucial, something implicit in his method of maxima and tangents. It would later be called the derivative. Its applications would go far beyond curves and their tangents to include any sort of change at all. The crossroads. We have come to a crossroads in our story. This is where calculus becomes modern and progresses from the mystery of curves to the mysteries of motion and change. It's where calculus starts to wonder about the rhythms of the universe, its ups and downs, its ineffable patterns in time. No longer content in the static world of geometry, calculus becomes fascinated with dynamics. It asks, what are the rules of motion and change? What can we predict about the future with certainty? In the 4 centuries since calculus reached this crossroads, it has branched out from algebra and geometry to physics and astronomy, biology and medicine, engineering and technology, and every other field where all is in flux and change never stops. Calculus has mathematized time, and it has offered us hope that the world we live in, for all its unfairness and misery and chaos, may be reasonable deep down, deep in its heart, where it follows mathematical laws. Sometimes we can find those laws through science, sometimes we can understand them through calculus, and sometimes we can use them to improve our lives, help our societies, and change the course of history for the better. The pivotal moment in the story of calculus occurred in the middle of the 17th century, when the mysteries of curves, motion, and change collided on a 2-dimensional grid, the XY plane of Fermat and Descartes. Back then, Fermat and Descartes had no idea